Hi guys, it's time to talk a little bit more about bonds tonight, but not these bonds. Tonight we're going to be talking about these bonds. Not ionic, but covalent. Remember, you should have your notebook out and ready to go. Anything that's written in red other than these bonds right here, you want to make sure to jot down in your notebook for our flipped notes on covalent bonds. So again, tonight we're going to be starting with B, covalent bonds. Now, a nice way to remember what covalent bonds are is remembering something we learned in kindergarten. And here's a nice little button here. Sharing is caring. Now with covalent bonds, the sharing is caring means that we're not giving and taking like we do in ionic bonding. We're sharing. So instead of passing those electrons off, the electrons that are needed are gained by sharing equally. So covalent bonding is when atoms share electron pairs to fill up their outer valence shell. Let's go ahead and take a look at water because water is a great example of covalent bonding. Each of my hydrogens here kind of looks like Mickey Mouse. Each of my hydrogens have one electron. To fill up that first outer valence shell, they need to gain one more. My oxygen in its outer valence shell, it's in group 6, means it has 6 electrons and it needs 2 more. So the way that my 2 hydrogens and my oxygen become happy is that my oxygens and hydrogens each share an electron pair. And you can see here, hydrogen's full, and if you count out the electrons in oxygen's outer shell, you get 8. So each atom shares an electron with oxygen. Now with covalent bonding, it's important to note that sharing is always equal. So if one atom shares an electron with another atom, that atom is going to share one back. So you have sharing in terms of 1 electron and 1 electron, called an electron pair, 2 electrons and 2 electrons, 3 and 3, and in some special cases, we have sharing of 4 and 4. Now, the reason we have sharing is because covalent bonding always occurs between a nonmetal and a nonmetal. If you think back to ionic bonding occurred between a metal and a nonmetal. Now, nonmetals, as we learned in my last flip video, they're highly electronegative. That means they're very, very attractive to electrons. They don't want to give up what they have. So if you have 2 atoms that don't want to give up what they have, but they still need to get a little something, they get that by sharing. So the electronegativity piece is a really good way to remember what type of bonding is going to take place. Now, we have a few different types of covalent bonds that we're going to talk about tonight. The first type we're going to start by looking at chlorine gas. So chlorine forms a covalent bond with itself and it forms a molecule of chlorine gas called Cl2. So how will 2 chlorine atoms combine? To figure out how they're going to combine, we want to look at the Lewis dot structure of each of our chlorines. They're in group 7, so they each have 7 outer valence electrons, which means they need to gain 1 electron to achieve their octet. Remember, the octet is that full outer valence shell, and that's when we know we're stable, and that's the goal of bonding. So neither atom is going to give up an electron because chlorine is highly electronegative because it's a nonmetal. So what's the solution? What can they do to achieve an octet? Well, they come together like this. There's my octet. There's my octet right there. The way we know that our octet is full is we circle it kind of like a Venn diagram, and then the area in the center represents the amount of electrons that are being shared. In this case, we have an electron pair in the middle, so the overlap between the two is going to be our pair that's shared. We call that the sharing ground, and we always want to make sure that the sharing ground is in between both of our atoms, because if you're sharing something, you want to make sure both atoms can reach what is being shared. Because there's just one pair, that's called a bonding pair, and it's a single bonding pair because there's one. So this type of bond is called a single bond. So when a single pair is shared, it's called a single bond. And we can also denote that using a single dash like that. So one dash is representative of a single bond. So let's go ahead and get this into our notes. A single bond is when 1 electron pair is shared. This is our electron dot diagram of the covalent bond, and here's our abbreviation of it using our single dash right there. Pause me at any time if you need to make sure to get the notes down accurately. So let's look at a different type of bond. And we'll go ahead and take a look at oxygen. Oxygen's pretty important for life on Earth, and that is our molecule O2, also called a diatomic molecule like chlorine. The di means two, and then the atomic part means of the same atom. So anytime you have a diatomic molecule, it means you have two of the same atom hooking up together to form a molecule. So how will my two oxygen atoms bond? Let's kind of look at it the same way we did chlorine. We're going to start with my electron dot diagrams. Both oxygens are in group 6. Obviously, they're both oxygen, which means they have 6 outer valence electrons. So now let's think of how many unpaired electrons there are. Well, it needs 2 more electrons to be full, each one, which means it needs to pair up 2 of its electrons. So keep that in mind as we walk through this. Each atom has 2 unpaired electrons. Oxygen atoms, remember, are highly electronegative. They don't want to give up any of their electrons, so they want to gain 2. So 2 pairs are shared in this case. And then we bring both pairs into the sharing ground. You can see them circled right there. So when we circle my octet, we circle the entire sharing ground. Count those electrons in my octet, and you're going to get 8 of them on this side. And then if we look at my octet on the other side, it's full with another 8. It's got to have 8 in that circle. That's going to let me know that we achieved stability. The double bonding pairs makes a double bond. So this is not a single bond, but a double bond. And we show that with a double dash. So here's my double bond notes. A double bond is when 2 electron pairs are shared. Those 2 electron pairs both in my sharing ground right here. But each octet, as you guys can see right here, has my 8 electrons in it. And then there's my abbreviation of my double bond. Okay, last but not least, we're going to look at my last type of bond we're going to talk about. And this could happen between nitrogen and nitrogen. So the same way we walk through the other ones, go ahead and find nitrogen on your periodic table. And you're going to see that it's in period 5, which means that each of my nitrogens have 5 outer valence electrons, which means each of them need 3, which means each of them are going to share with each other 3. So it's not a single, it's not a double, it's a triple bond. And I forgot a little number here that's pretty important. So you're going to write triple bond is when 3 electron pairs are shared. And we show that with either 3 dashes if I ask for the abbreviated form, but mostly we're going to be drawing our Lewis dot structure form down here. And again, you'll see in my sharing ground I have 1, 2, 3 pairs being shared in that overlap area right there. And then these 2 on the side are the ones that each atom kind of keeps for itself. It's not sharing those ones right there. Okay, now what do you guys notice about the type of covalent bond formed between chlorine, oxygen, and nitrogen and their location on the periodic table? Because there's a trend that hopefully you've kind of figured out a little by looking at it. And what you may have noticed is that chlorine is in period 7 and it needs 1 electron, and because of that it forms a single bond. Oxygen's in period 6. Because of that it needs 2 electrons, forms a double bond, and then we just figured out nitrogen's in 5. It needs 3 electrons, and because of that it forms a triple bond. This is also related to their oxidation number, so you can write an oxidation number on top of each one of the groups, and that tells you how many electrons, remember, if you look back in your notes, need to be gained, lost, or shared in this case to be full. So anytime you have an element bonding with itself or another element in the same group, in groups 5, 6, and 7, the oxidation number is going to be the type of bond that forms between them. So here's just one more example of a covalent bond, and in this case it's not diatomic. Here's my water. We looked at this one already, and if you remember, we're going to put oxygen in the middle because it needs the most number of electrons to be shared in order to fill up. And then we have my 2 hydrogens on either side. So think of our Lewis dot structures for all 3 of these, and what we come up with is sharing in this case. We have my hydrogen sharing 1, oxygen shares 1 back, and then on this side, hydrogen shares 1 and oxygen shares 1 back. And you can see my circles showing my full octets, and everybody's happy. Now, remember we talked about sharing is caring? Well, in some cases, actually, sharing isn't always equal. And in the case of water, it isn't always equal. Because if you look at electronegativity increases as we move from left to right across the periodic table, which means that oxygen is more electronegative than hydrogen. And my definition of electronegativity, remember, is attractiveness to electrons, which just means that electrons like oxygen a whole lot more than they like hydrogen. So here's my trends table, and you can refer to this when you're looking at covalent bonding between molecules to figure out how equally they're going to share their electrons. So here's my water. What ends up happening with water is because oxygen is more attractive, it holds the electrons a little closer and it pulls them a little further away from hydrogen. When it does that, my oxygen side of my water becomes slightly negative because those electrons are closer, and my two hydrogen sides become a little more positive because that proton force in the nucleus is more positive and the electrons are further away. We call this a polar molecule, and we've talked about this a little bit in science class. So anything that's water-based is polar, and that's just a molecule that has slightly negative end and a slightly positive end. And because of this, electron pairs are not shared at equal distances from each other. Now, overall charge of my molecule is still neutral. We show this polarity. Oh, there's my cool little cartoon on the evil chlorine pulling the electrons closer from hydrogen, just to help remember polar. We show polarity with the sigma symbol, and you put a little sigma plus on the side that's more positive, so that's the one that is not as electronegative, and then the one that's very electronegative is going to have the sigma minus. They're going to be more attractive to my electrons. Last but not least, almost done with tonight's video, we have nonpolar. So nonpolar is the opposite of polar, and actually that should be a lowercase d right there. So nonpolar is when we do share equally. So it's a molecule in which electrons are shared at equal distances in bonds, and we don't get those positive and negative sides. So nonpolar things are things that don't dissolve in water. So if you think back to our density lab, that would be oil. Oil does not dissolve in water because it's nonpolar. It doesn't have those positive or negative ends, so it's not attractive to water. It's actually repelled from it. And if you look at our density columns in class when you guys come in next period, you'll see very clearly how stratified the oil is from the rest of the liquids we worked with. And here's my last cartoon, polar, two hydrogens, very happy sharing electrons equally in the center. Make sure you bring those notes into class, and we'll be talking about covalent molecules when I see you guys next. Have a great night.